Very good afternoon. This is the lecture number 3 in this series. What we can say, the topic is Learning IS 1893 2016. As you know, this code has been developed very recently. So we need a training program to learn the ins and outs of this code. So this program has been divided into two parts. The first one is of today, and the next one is a continuation of this code, which will be held on 29th of this month. So those who are joining today should logically join the next program also on the 29th. In the meantime, just a little bit of information. We are also organizing one offline seminar in Calcutta. So those participants who are in Calcutta and wish to join the seminar on 22nd of July must contact us very fast so that they can be registered. So this is happening after a gap of 5 to 6 years. And the topic is use of high strength steel in construction. So that's an interesting feature which we are organizing coming Friday. So before we start the program, I would like our Director General, Mr. P.K. Mishra, to say a few words. So over to Mr. Mishra.
Thank you, Mr. Ghosh. Once again, Dr. Jain, my warm welcome to you for this lecture series. We are really grateful to you that you are conducting this series, and my greetings to all the participants. The participants who are already joined, some of you may be knowing about INSTAC, but I still feel I must share a few information about this institute. The Institute for Steel Development and Growth. This institute is authorized on INSTAC, is in existence for last 23 to 24 years. They are in operation, and the main objective of the institute is to help in promotion of usage of steel in the country. That's the main objective. Different type of applications of steel, in particular in construction area, and again we are also participating in making of various BIS and IRC codes. We have made about more than 100 publications during last 23 years, and some of the skilled professionals are available in this institute. So, and as of now, we are trying to really make a very structured, very concerted effort to disseminate knowledge about the whatever little expertise this institute has. We want to share among the students, the professionals, and get their suggestions how to improve the working of the institute. In fact, there is a feeling that the institute should be more visible, it should be more useful for the stakeholders, and I fully agree with that. So this is through this kind of interaction, I would like to request all the participants, the professionals, the academicians, the professors to advise us, to suggest to us how we can make this institute more useful for the stakeholders. For your information, as on date, we are having a few initiatives which you'll be very happy to note. One, we are going to launch our new website on 22nd. Mr. Ghosh just now told that we are holding a seminar. That we are going to launch a new website where you will have a training calendar. In fact, the areas where our people have got expertise, where they can share the information, the knowledge that whatever the institute has gathered over the years, that can be shared with the professional. So we have made a training calendar which will be displayed in the website. You can see it from 22nd onwards. So anybody who is interested to get information about the training or happenings about the institute, he can log into the website. Second, we are also doing, we have started initiative that is, there is always an inquiry. I have during last 5-6 months, I have seen a lot of people are making inquiries. How do they make steel buildings, steel-based buildings? They know the benefits of steel. They know that steel buildings are a kind of success story in other advanced countries, but many of them don't know how to make a steel building, whom to approach, who's contractor or designer going to help them. So what we have started, we are offering our services as a one-stop solution for providing right from design to construction, design to execution of steel-based structures. INSTAC has taken up that responsibility, and we have already offered our services to Steel Authority for their, two of their projects. Bamanlari recently has also, made an inquiry, and we are also helping them how to go for steel instead of usual conventional concrete. So my request to all of you, whenever you find that there is an inquiry for this kind of steel-based solution, please remember us, please recommend us. Number two, we are also very, proactively trying to work on this life cycle cost analysis, because life cycle cost analysis of steel is very important, because that will help us to influence the government to make LCC mandatory in their tender provisions, because as of now it is not mandatory. That's the reason why most of the people go for concrete. So that LC study also we are trying to do. We are also trying to launch a certificate course with the help of Jadavpur University here locally, so that the engineering students who are in the final year who want to join the job, they can also pick up some skills through the certificate course, and they become, market worthy, job worthy. So they, their market value goes up. So that kind of certificate course also we are planning. So there are a few initiatives we are taking, but I will request all the participants, particularly the academicians and the professionals who are participating here, please give your suggestion. Please help us to improve our working, so that this institute, which is a unique institute only for the cause of promotion of steel, becomes more useful for the stakeholders. Thank you.
Thank you, sir. Thank you for your kind words. Now, before we start, a little bit of background of Dr. Ashraf Kumar Jain, though he does not require any new acquaintances. So, Dr. Ashraf Jain obtained his BSc from Meerut University in 1968, BE Civil with honors from University of Roorkee in 1972, ME Structures with honors from University of Roorkee in 1974, and PhD from University of Michigan, USA in 1978. He is a recipient of several gold, silver, and bronze medals from the University of Roorkee. He joined University of Roorkee in September 1979 as a lecturer and became professor of civil engineering in 1991, and later served as head of the department. He was the director of MNIT Jaipur from 2003 to 2005. He retired from IIT Roorkee in May 2016. His main areas of interest includes multi-storied building, towers, bridges, earthquake-resistant designs of RC and steel structures. He has authored 5 textbooks on structures and computers. Dr. Jain published over 145 papers in reputed national and international journals and conferences. He carried out pioneering work on the post-buckling inelastic response of steel bracing members and concentric braced steel frames. He is the fellow of the Institute of Engineers and Indian Association of Structural Engineers, life member of Indian Concrete Institute, Chennai, and Indian Society of Earthquake Technology, Roorkee. Dr. Jain is consultant in many agencies in the area of structural engineering and earthquake-resistant design. This is, in short, the CV of Dr. Jain. Now, I would request Dr. Jain to start his presentation. Thank you.
Thank you, Mr. Mishra and Mr. Manas, for such nice words. It's my pleasure to be here with you to discuss the salient features of this Earthquake Code 1893. before I go to the 1893 code directly, let me give you a little bit of background. I hope you can see my screen. Hello, I hope everybody can
Yes,
see
sir.
my
Yes, sir. It's visible.
Okay, okay, thank you. Now, as far as this 1893 code is concerned, it has three features built into this code. One is it tells you what should be the shape and other characteristics of a building, that is in terms of mass distribution, in terms of stiffness distribution. Second aspect is it tells you how to calculate the earthquake force on a given building at a given site. That means in a given seismic zone. And thirdly, it tells you how to analyze the building for a static case as well as for dynamic case. So these are the three distinct areas which are covered in this 1893 part 1 code. Okay. Now, before I come into this code directly, my experience says that most of the people, they do not have a sufficient background or no background at all of dynamics of structures. They have studied a course on earthquake design in their undergraduate course. So they know how to carry out the analysis and design a building, but they don't have the necessary background from the point of view of dynamics of structures. Okay. They've only done static analysis, but not the dynamic analysis. And therefore, there are a lot of things which are not clear to them, and they cause a lot of problem in trying to understand the salient features of 1893 code. So what I will do today is first of all tell you about what is the multi-degree freedom system, how it is simplified, what are the mode shapes, what is the meaning of mode shape, and what is the meaning of frequency and so on. And then I will tell you how to analyze a building for static and dynamic analysis. And on my next term, that is on 29, I will talk about the various clauses of 1893 code. I hope this part is clear to you. So in multi-degree freedom system, that means any multi-story building is classified as a multi-degree freedom system. It has number of degrees of freedom. Okay, that's why it's called multi-degree freedom system. Now, the mathematical modeling of a multi-degree freedom system can be done in three ways: using lumped mass model, using influence coefficient model, and using finite element model. Now, most of the time, we either use a lumped mass model, which is the simplest and gives you fairly accurate, fairly reasonable results. And a little more advanced model is called influence coefficient model. Okay, finite element model is also very most accurate, but it needs much more understanding of the subject of finite element method, how to analyze it, how to model it, and then what are the other complications associated with finite element method. So that finite element model is used only for very specialized buildings like nuclear power plants or some other structure, or maybe the dams. Okay, but for most of the buildings, we use is a lumped mass model or influence coefficient model. Okay. What we do in a lumped mass model, we represent a building by a series of springs and masses. This is also referred to as a lumped mass system. All the masses on a given floor are lumped together. Similarly, stiffness of all the lateral load resisting elements in a story are lumped together. Damping is neglected in this present formulation. It is assumed that there is only one lateral degree of freedom per floor. If there are 20 stories in a building, it will have 20 degrees of freedom. If there are n stories, there will be n degree of freedom. And if the system is allowed to vibrate freely, it will vibrate in natural mode or what we call as normal mode. It means the system has exactly the same number of modes as the degrees of freedom. A natural frequency and a characteristic shape, diffracted shape is associated with each normal mode. A salient feature of this normal mode is that the system could, under certain conditions, vibrate freely in that mode alone. And during such vibration, the ratio of the displacement of any two masses is constant with time. The complete motion of the system can be obtained by superimposing the independent motions of the individual modes. And this particularly forms the basis of the solution of multi-degree of freedom systems. That's how this model looks like. It's called spring mass system. Each story, the mass is lumped at one point, the whole stiffness of that one floor, the lateral stiffness is lumped at one point by using one spring, and then we'll find out the free-body diagram of each mass, which is shown here on the right-hand side. Then we can write down the equations of equilibrium for each mass separately. And if there are n degrees of freedom, you will get n equations, and we can combine all these equations, which is shown here by m n by n x double dot plus k n by n x n by 1 is equal to 0. That is mx double dot plus kx equal to 0, and n is the number of active degrees of freedom of this particular system. Okay, this is a free vibration case. Right hand side you can see is 0, so it is known as free vibration case. That means the building is going to vibrate in its free motion. X double dot represents the acceleration, and x represents the displacement. So it can be written like that in simplified form: mx double dot plus kx equal to 0. We have shown it by bold and capital letters because a bold and capital letter represents a matrix. So here mass m, stiffness k, each represent a matrix, and x double dot represents the displacement and acceleration respectively. Now, it should be remembered that vibrations in a normal mode must always be a harmonic motion. That means sine theta or cos theta. It was already stated earlier that during the vibration in a single mode, the displacement of several masses are always in the same proportion. That is, all possible positions are geometrically similar. All masses vibrate in phase with the same natural frequency. So you make some assumptions, that is, displacement x1 is equal to phi1 sine omega t, and x1 double dot is equal to, you can differentiate it twice to get acceleration x1 double dot is equal to minus omega square phi1 sine omega t. Similarly, x2 is equal to phi2 sine omega t, and x double dot 2 is equal to minus omega square phi2 sine omega t, and so on. We differentiate all the n values, and this set of equation called is equation B. Okay, this can be written again in the matrix form, that is shown here, and then we can simplify it and substitute in the earlier equation. And that's how this matrix looks like. This is K1 minus M1 omega square. This is the N by N matrix. Phi1, phi2, phi3, phi n is equal to 0. And this set of equation can be arranged in matrix notation as follows: K minus omega square M square bracket 5 n into 1 is equal to 0. Now here, this is a very, very important equation, and this is very important. See, I don't expect you to understand the mathematics behind it. Okay, I'm showing mathematics only for the sake of completeness, and those of you who want to understand the mathematics, they can refer any book on dynamics of structures, and they will be able to appreciate what I am trying to say here. Now, the reason I showed you this equation, equation 1.5, which you can see on my screen, is because this is the most important equation, and because most people don't know the background of this equation, therefore they find it very hard to understand the various clauses of IS 1893 code. Okay, so that is the reason I'm trying to give you that background so that the code becomes clear to you. Now, in this equation, you will find that there are n plus 1 unknowns. How there are n plus 1 unknowns? There are n values of phi's. You can see here phi n by 1, phi 1, phi 2, phi 3, phi n, which are the coefficients of x1, x2, x3, xn. So this is phi is known as mode shape coefficient, and there are n values of phi which are unknown. And another value which is also unknown here is omega. As far as matrix K is concerned, it is known to us because we know what is the size of each beam, each column, each wall. Okay. We also know the material, whether it is concrete, whether it is steel, or whether it is a mixed construction. So we know the modulus elasticity, we know moment of inertia, we know area of construction, and so on. So its stiffness K is fully known to us. Similarly, mass. Since we know the size of the matrix of each element, we know the density, therefore we know the weight and therefore the mass of each element in our building. Okay, so K and M are fully known to us. What is unknown is n values of phi and one value of omega, which is the frequency. Okay, so there are n plus one unknown total. But our problem is we have only n equations with us, because n equations we get by considering the equilibrium of each of the n masses corresponding to each story. So there are n stories, we have n degrees of freedom, and therefore we have n values of phi which are unknown to us. And the n plus 1th value is omega. Now our problem is if there are n equations and n plus 1 unknown, how do we solve this equation? Okay, so what we do is we assume one value of the displacement, say x1 is equal to 1. And by assuming this one value, we can solve the remaining n plus 1 values. I hope this point is clear. We assume one value of x, let's say x1 as 1.0, just an assumed value. And now we find the values of 5, 2, 5, 3, 5, 4, up to phi n. That means we are left with n minus 1 values of phi and one value of omega. Okay, so what it means is when we get the value of phi and we put in the x, that is, if you go back to the earlier equation, see here, x1 is equal to phi 1 sine omega t. So omega is known, phi 1 is known, therefore x1 is known. Similarly, phi 2 is known, omega is known, x2 is known. But because we assumed the value of phi 1 as 1, therefore all the values of phi 2, phi 3, phi n and x1 to xn, these become relative values. So although this is a displacement, x1 is displacement, x2 is displacement of mass 2 in story 2, and xn is the displacement of story n. Okay, but all these displacements become relative because x1 was assumed as 1, and there is no way we can calculate n plus 1 unknowns by using n equations. Okay, so I hope this part is clear to you, and therefore these phi values are known as mode shapes, and they don't have any unit. They don't have the unit. See, displacement should have normally the unit of millimeter or centimeter or meter. Okay, but because we don't know the absolute values, we know only relative values of phi 1 to phi n. Therefore, they call it mode shapes, and there is no unit assigned to it. Okay, because they are all relative values. If x1 is 1 millimeter, you may say those are millimeters, but it has no meaning because those are all relative values. Now, if this equation 1.5, actually this represents a polynomial of the order n. Okay, so we can plot this polynomial, and that's how this polynomial will look like. Okay, and wherever this polynomial has 0 values, that gives you one value of omega 1. Second root gives you, so there are n roots corresponding to each of these points of intersections. So what we get is, we get n values of omega, that is omega 1, omega 2, omega 3, omega 4 up to omega n. Okay, and this equation, that is this equation here, as well as this equation ms double dot plus kx equal to 0. This is called frequency determinant or characteristic equations. Upon simplification, we get this polynomial of order n in omega square. That is the value which we get here, and we plot it, find the solutions. Okay, the nature of the mass matrix, damping matrix, and external matrix, whether they will be diagonal, banded, full, and real or complex will depend upon the physical problem that you are trying to solve. In any case, one thing is for certain, the external matrix will always be a coupled matrix as I have shown in our equation. The mass and damping matrices may be coupled or uncoupled depending upon how you have done the formulation. The solution of the equation of motion will depend upon the nature of the constituents and size n. Therefore, there are several algorithms available in the literature for the solution of this characteristic equation. One has to select a appropriate algorithm, most efficient algorithm to suit your given problem, because same algorithm may not work in all the cases. Okay, now the determination of natural frequency and mode shapes of a multi-different system will be discussed in the next section. Now, the various stages of simplification of a multi-different system are shown in the flow diagram, as I'm going to show you just now. So we try to simplify our multi-degree freedom system in this manner. So first of all, we take a multi-degree freedom system and write down the equation of undamped free vibration, that is m x double dot plus kx equal to 0. Why you call it undamped? Because damping is taken as 0. It is an assumption. In real life, damping will never be 0. Okay, but here we assume damping is 0 for simplification. Okay, to make our life easy. Free vibration, we are not applying any force on it. The external force is 0. The building will vibrate under its own characteristics. Okay, so we get this equation here. This equation, which is the polynomial of degree n in omega square. This is the frequency equation, or this equation is also the same thing, k minus omega square m, phi is equal to 0. This is in the matrix form, and this is in the polynomial form. And we solve this, we call it eigenvalue problem, which is ax equal to lambda x. This is the standard form of eigenvalue. Okay, lambda is the frequency or eigenvalue, x is the eigenvector or mode shape. Stage 2, we use some more characteristics of the mode shapes and develop a orthogonality condition of mode shapes. Then we do the scaling of the mode shapes. We get the normal coordinates, and then they reduce the system n by n system to n by p system. What it means is, if you have a multi-different system having, let's say, 500 degrees of freedom, the question is, do we need to find out all the 500 frequencies and 500 mode shapes, or we can get away by finding only, let's say, 5 frequencies and 5 mode shapes instead of 500 mode shapes and 500 frequencies. Okay, so to make our life easy, we choose a parameter p or a number p. We say, instead of n modes, we will consider into our calculation only p modes, where p is very small number as compared to n. Usually 3 mode shapes will be sufficient for most of the buildings, or 5 mode shapes, at the most 10 or 20 mode shapes. We don't have to go to determine more than those many frequencies and mode shapes. What is the advantage? The advantage is our calculation becomes very fast. We have very powerful algorithms which will give us first few frequencies and first few mode shapes very quickly. Okay, so that is the reason why we want to simplify a multi-degree freedom system like this. The undamped free vibration analysis. As I said, in undamped, C is 0 and the external force is 0, and we have this equation mx double dot plus kx equal to 0, and we can simplify it and develop the equation kx equal to lambda x, or a phi is equal to lambda phi. Okay, and this is again a characteristic equation. Okay, now once we understand that we can simplify this multi-different system into eigenvalue problem and find out first P frequencies and P modes. Let's come to this building. Now this is a 4-story building having mass M1, M2, M3, M4 lumped at each floor. K is the K1, K2, K3, K4 are the lateral stiffnesses at each story. Okay, so on the right hand side, what you see is the mathematical model. On the left hand side is the physical building. Okay, now how the mode shapes look like? The mode shapes look like this. The first mode is shown first, then mode 2, mode 3, mode 4. Now, please try to understand what is the meaning of these mode shapes and how do we get these mode shapes. Okay, we get these mode shapes by the frequency analysis or by the solution of the characteristic equation which I just mentioned to you. Okay, now mode 1 looks like this. Now, what is the characteristic of mode 1? The characteristic of mode 1 is the entire building is deflected either to the left. See, the vertical position is the mean position. Okay, so the whole building is deflected either to the right or to the left of this mean position. So the top displacement is 1.0, and relative to this, the next floor displacement is 0.88, third is 0.652, fourth is 0.347. Okay, now what you see here in the mode 1 is that this deflected shape does not intersect the mean position. Okay, what happens in the mode 2? Partly the building is to the left and partly the building deflects to the right. That means on the top floor, the displacement is -1, that is minus is to the left side. Then at the second, at the next story, the displacement is 0, which happens to be 0 just by chance. Third story, the displacement is 1.0 to the right. And again, fourth story also has a displacement 1 to the right. Now, as far as the minus and plus signs are concerned, these are arbitrary signs. You can say that the displacement to the right is minus and displacement to the left is positive. Okay, so in mode 2, you find that the deflected shape intersects the mean position once. That happens to be at the third story from the top. Okay, third mode, you can see the displacement, the building is deflected to the right, to the left, again to the right. So 0.652 minus 0.88 minus 0.347, 1 to the right again is mode 3. So in mode 3, the deflected shape intersects the mean position 2 times, 1 less than the mode shape. Okay, and the mode 4, it will intersect the mean position 3 times, 1 less than the mode shape itself. So in fourth mode, the building will the building will deflect and intersect the mean position 3 times. In third mode, the building will intersect 2 times. Second mode, it will intersect only once, and in the first mode, it will not intersect. The whole building will deflect either to the right or to the left. So I hope these mode shapes are very clear to you and how we have obtained these mode shapes. Okay, so first mode shape, second mode shape, third mode shape, and fourth mode shape. These are simplified methods of analysis of degree freedom system. Okay, and what are the frequencies? The first frequency happens to be 0.346 square root k by m. Second frequency is 1 times square root k by m. Third frequency is 1.53 square root k by m. And fourth frequency is 1.88 square root k by m. So these are the first 4 frequencies, 1, 2, 3, 4. And because we have a 4 degree freedom system, there are 4 frequencies and 4 mode shapes. Okay, so it means it can be interpreted that we have decomposed a 4 degree freedom system, that is a multi-story building having 4 stories. We have decomposed it into 4 single degree freedom systems. Each the system has these diffracted shapes which are shown on my screen, and these are the frequencies of each of those single degree freedom system. So it is a equivalent single degree freedom system. We can find the response of each single degree freedom system, and then we can combine by carrying out mode superposition method to get what is the total response of this building. Let's take a 15-story building. Okay, so what I have done for this 15-story building, I have carried out an analysis and I'm showing you here first 10 modes. Again, as far as the first mode is concerned, the first mode, it does not intersect the mean position at all. The second mode will intersect the mean position once. The let's say the sixth mode will intersect this mean position 5 times. And the 10th mode shape will intersect the mean position 9 times, one less. So by looking at the mode shape, you can tell immediately which mode shape it is. Okay, so in a 15-story building, we don't have to calculate all the 15 stories, 15 mode shapes and frequencies. You can just calculate first 3 mode frequencies or 5 frequencies, depending upon your choice. Okay, and here I have shown you the frequency in hertz, that is cycles per second. The first mode frequency is 0.689 and the period is 1.45 seconds. So what is the period? T period is known as T in seconds. That is time taken to complete one cycle. Okay, frequency is number of cycles per second. Okay, and if you find out 1 upon frequency, that you will get period, time period. Okay, so first mode frequency is 0.689 hertz, second mode is 2.0, third mode is 3.49, fourth mode is 4.94, and so on. Similarly, you see here the first mode is 1.45 seconds, second mode is 0.48 second, seventh mode is 0.103 second. Now what it tells you? It tells you that in terms of frequency, the first mode, which is also known as fundamental mode of vibration. Okay, first mode, which does not intersect the mean position at all, is known as fundamental mode of vibration. Okay, now in terms of frequency, the first mode will have the lowest frequency always. It is a universal truth. The first mode will have the lowest frequencies always, and it will also have the highest period because T is inversely proportional to the frequency. Okay, and as you go to the higher mode, say in this case, 7th mode is the highest, and the frequency is highest 9.624 hertz, and the period will be 0.103, which is the lowest, because again, omega, this frequency is F and T are inversely proportional to each other. Okay, so this is again a very important observation, that the fundamental frequency will be the lowest for the first mode, and the fundamental period of vibration will be the highest for the first mode. Okay, and as you go to the highest modes, though frequency will be the lowest, frequency will be the highest, and period will be the lowest. Okay. So if you have any questions in this frequency and mode shapes, please let me know. No questions in this part? Okay, then I will move to the second part of my lecture, that is the analysis of buildings for earthquake force. Okay, what are the characteristics of the buildings? That I will discuss on the next term. Today I will discuss how to calculate the earthquake force and how to analyze a building for the earthquake force. Now, as far as the force is concerned, in science, in physics, it is defined as a product of mass and acceleration. Okay, during an earthquake, the mass is imparted by the building, whereas the acceleration is imparted by the ground disturbance. Okay, what it means is, once you decide the various sizes of beams, columns, walls, etc., the mass of the building is fixed. Okay, because sizes are fixed, material is fixed, density is fixed, therefore mass is fixed. Okay, now you place this building anywhere you want on the earth, whether it is Guwahati, whether it is Sikkim, whether it is Chennai, whether it is Kolkata or Srinagar, Kashmir. Okay, now as far as the mass is concerned, this is fixed by the designer. What about the acceleration? acceleration is fixed by the nature. Okay, depending upon where your building is situated geographically. Okay, and what is the seismic condition of that particular location. Depending upon that, during an earthquake, the ground acceleration is decided by the nature, not by us. We have absolutely no control over the ground acceleration. Okay, that means as far as the earthquake force is concerned, it is a product of mass into ground acceleration. Mass is under our control, but not the acceleration. So if you want minimum force, the mass of the building should be as low as possible. And that's the reason why our forefathers used timber buildings and not masonry buildings or adobe buildings, because timber was the lightest material. Okay, it will give you the minimum earthquake force. Okay, as far as the ground acceleration is concerned, we have no control because it's supposed to be an act of God. Okay, now the point of application of the inertial force, this is called inertial force. I'm into acceleration, mass into acceleration, you know, the Newton's law, and this is the inertial force. This will act at the center of gravity of each floor, center of gravity of the mass of each floor. Okay, once there is a force, there has to be an equal and opposite reaction to balance this force. The inertial force is resisted by the building, and the resisting force acts at the center of rigidity, or that means center of gravity of the lateral stiffness of each floor of the building. Okay, the return period is another term. The return period of an earthquake in a given region depends upon its seismicity. Earthquake is generally classified into one of the three general categories. It's a very general definition, but very powerful, and it is used all over the world in all the codes. Minor earthquake, it may occur frequently, say every 5 to 10 years. Minor earthquake means its ground acceleration is very, very small. Okay. Moderate earthquake, it may occur, say, once in 20 to 30 years. Okay, these numbers are only approximate. Okay, these are qualitative numbers, and it tells you a moderate earthquake will occur in every 20 to 30 years. A severe earthquake, it may occur once in the lifetime of a building, that is once in 75 years or 100 years. Now, as far as the minor earthquake is concerned, in terms of damage, this minor earthquake is expected to cause only some damage to the architectural components of the building, some fascia or some jali or some decorative material, which is architectural nature, not structure. Okay, no other. And if there is a damage to these architectural features, it can be repaired easily. Moderate earthquake, it means there may be very fine cracks, structural cracks in a structural member, that is beam, column, or a wall. It may be masonry wall, it may be a RCC wall, it may be shear wall, or a steel frame. We may have some damage to the beams, steel columns, and bracing members. Severe earthquake, it may occur once in a lifetime. It means there will be a severe damage to the steel beams, steel columns, steel bracing members. There will be plastification at different locations, or the RC beams may have severe damage. The beams may fail, columns may fail, and so on. But the only requirement is, in a severe earthquake, the structural system should not fail. The structure should remain standing. The reason is, life is very important to us. We should be able to extract each and every life as far as possible from that building. And once all the people are out, then the building may have to be demolished. It's okay with us. Okay, we don't care as far as the building is concerned. Okay, but we want our structural design should be such, should have so much ductility available in it, so that in a severe earthquake, we should be able to save as many lives as possible. Possibly all 100% lives should be saved. Now, there are two methods to analyze a building. One is called static method or seismic coefficient method. Okay. Other is the dynamic method or response spectrum method also known as modal analysis, MODAL, modal analysis, or spectral acceleration method. There's two methods, static method and dynamic method. Okay. Now, there are two definitions of the earthquakes. One is the maximum considered earthquake, MCE. Now, this definition was there in the 2002 edition of the 193 code. It has been deleted in 2016 edition, which in my opinion was a very irresponsible act. It shouldn't have been deleted. We need the definition, and therefore we must understand what is the meaning of MCE. It is the largest reasonable conceived earthquake that appears possible along a recognized fault or within a geographically defined tectonic province under the presently known or presumed tectonic framework. MCE is an upper bound of the expected earthquake in a given area. It has a 10% probability of accidents in 100 years. Other term is DBE, that is design basis earthquake. It is that earthquake which has a 10% probability of accidents in 50 years. It can reasonably expected to occur at least once during the design life of a structure. It is assumed to be 1/2 of the MCE. So if you know what is MCE, you divide by 2, you get DBE. Now, this factor half is arbitrary, pure arbitrary. In other codes, it may be 2/3 or 1/3 or some other number. So I will tell you later on how we get these numbers. Now, as far as the modeling of a building is concerned, earlier when the computers were not available or we had very small computers, therefore it was common to carry out 2D analysis, 2D plane frame analysis of a building in each of the two orthogonal directions. In each plane frame, masses may be lumped at the 4 levels, with each mass having a 1 degree freedom, that of lateral displacement on the direction under consideration. Alternatively, a building may be modeled as a 3D space frame, with each floor having 3 degrees of freedom, 2 orthogonal translations in the x and y directions, and 1 rotation. So all the 3 deformations, that is 2 orthogonal directions, rotation, translations, and 1 rotation about the vertical axis Z, they all occur in the horizontal plane. Okay. Now, with the availability of very powerful software and computing machines, 2D analysis is not done anymore. So we always said we go for a space frame analysis. Now, base shear. How do we calculate the base shear? See, in the early 1900s, when the earthquakes were occurring, in fact, earthquakes have been occurring since time immemorial. Okay, people were very, confused how to design a building for earthquake. In those days, there was no limit set, no working stress method, no formal education. Therefore, people were at loss how to design a building. So in Italy, Italians in early 1900 or maybe late 1890s, they thought of a number, say 10%. They thought that if we design a building for 10% of its weight applied in the lateral direction, let's see what happens during the next earthquake. And they found that if they design a building for 10% of the weight of the building, the 2 orthogonal directions, then during a severe earthquake, this building behaves pretty well. Now, that was a very interesting observation which they found by their experience and judgment. And then this concept was borrowed by Japanese. And later, the engineers of California, they have visited Japan and they found that they are using 10% formula. Okay. And they came to know that formula was originally borrowed from Italians. Okay, because Italy also has very severe seismic problem. Okay. So this alpha H here for a very severe seismic zone was taken as 10%. Okay, now that became a benchmark. That means in a severe seismic zone, we take alpha H as 10% of W, that is the dead weight of the building, or maybe some small live load also, and we get total earthquake force at the base of the building. Okay. Of course, that was at that time in 1900s. And now we have a much more better understanding of the earthquakes. We have a lot of instruments, and we have so much knowledge now of the materials and so on. Now the formula for alpha H is given by here, that is Z by 2, I by R, SA by G. Z is the zone factor for MCE condition, that is maximum considered earthquake. I is the importance factor, R is the response reduction factor, S is the spectral acceleration, depending on the period of vibration and damping of the building. G is acceleration due to gravity, and W is known as seismic weight. Now, seismic weight includes dead weight of the building and reduced live load. We don't take full live load. We assume that during a severe earthquake, we assume that the probability of having maximum live load also is very rare. Therefore, keeping in view the frequency of occurrence of an earthquake at a given location, we try to economize and say that we will take full dead weight of the building and part live load, or known as reduced live load on the building in our calculations for the design of a earthquake force. Okay. Now here we need one more term, that is the fundamental time period of the moment resistance. What is the fundamental time period of the building? You see, we have just discussed. We need to know what is the various fundamental frequencies in the first mode, second mode, third mode, and so on, and also what are the mode shapes. Okay. Now, as far as the seismic coefficient method is concerned, seismic coefficient method is generally applicable to buildings up to 40 meters in height or maybe 90 meters in height, and those are more or less symmetrical in plan and elevation. Okay. Seismic coefficient method, that is static method, is applicable to a building which is more or less symmetrical in plan and elevation with respect to geometry, mass, and stiffness distributions. It is based on the first mode diffracted shape of the building. Okay, we already discussed what is first mode, how it looks like. Okay, so the seismic coefficient method or the static method is based on the first mode diffracted shape, and it is responsible for about 70 to 80% of the dissipation of strain energy imparted during an earthquake. Okay, for most practical purposes, the static method of seismic analysis gives you reasonable estimate of the member forces. Now, to get the first mode for seismic method or the static method, we need to know what is the fundamental period of vibration. So, a number of tests were carried out in America in 1960s on various RCC buildings and steel buildings separately, and they carried out the test and plotted the results. Okay, and they found that they fitted curve fitting. By using curve fitting, they developed some equations. And one of the equations developed was T is equal to 0.075 h to the power 0.75, where h is the height of the building of the ground level in meters. And this empirical formula is a very simple formula. It gives you the fundamental period of vibration of a RC moment resistant frame building in seconds. Okay, 0.075 h to the power 0.75. Okay, that is the formula. It is a simple formula. This is based on first mode diffracted shape only. Okay, h is the height of the building in meters. For a steel building, that is MR steel frame building, moment resistant steel frame building, the fundamental time period in the first mode is obtained by the formula 0.085 h to the power 0.75. Again, h is the height of the building from the ground level. Okay, both of our equations were based on actual measurements in USA in 60s. The data were plotted on a graph, and lower and upper bound were determined using curve fitting techniques. What is the minimum time period? What is the maximum time period for the entire range? These equations represent lower bound values. The one I'm shown here, 2A and 2B, 0.075 and 0.085. This gives you lower bound, means higher earthquake force. The AC7 code, that is the American code, which tells you how to calculate the earthquake force on a building, which is equivalent of 1893 code. Okay, that will give you some relaxation to these values, because these are the lower values which gives you a very high seismic force. So they give you some relaxation in seismic force. But whereas the Indian code does not offer you any such relaxation, although these equations are borrowed from the American code. Now for RC frame building with infill walls, okay, or shear walls may be determined by the following empirical formula. T is equal to 0.09 H upon square root D, where D is the depth of the building in meters in direction of the earthquake force. That means if your building is rectangle, in X direction, its period will be different. In Y direction, the period will be different. H is the height of the building, which will remain constant in both directions. But length may be different, width may be different, therefore D will be different. Okay, so T will be different in the X direction and T will be different in the Y direction. This one thing must be remembered with this formula, that although our code writers of the 1893 code, they love this formula, T is equal to 0.09 H by root D. Although this formula was discontinued in most of the international building code, including the American code, where it was introduced in 1970. UBC code you must have heard of. The Uniform Building Code 1970 first introduced this formula in 1970. And in 2000, that formula was discontinued from that code. Okay, but today we are in 2022, and this formula is still being retained in our earthquake code, because this gives you the minimum possible time period, and minimum possible time period gives you highest possible earthquake force. Okay, so this formula is extremely conservative. It has been discontinued for almost all over the code, all over the international codes, except Indian code. Okay, it is because our code writers, they have a special love for this particular formula. Another formula which can be easily used, which is very powerful, called Rayleigh's method. This is the formula. This is based on the basic principles of dynamics of structures. This is a formula, and it gives you fairly reasonable estimate of the time period. This can be used both for MR frames as well as frames with shear walls or infill walls. Okay. Now coming to the seismic coefficient method, as I mentioned to you, this seismic coefficient method is based on the first mode diffracted shape. It is responsible for 70 to 80% of the dissipation of the strain energy imparted to the building during an earthquake. Okay. And let me tell you, whether the building is 40-story or 90-story, as long as the building is reasonably symmetric or it's a regular building, seismic coefficient method can be used very comfortably, and there is no need to worry about whether it is unsafe or not. This seismic coefficient method is very reasonable, gives you pretty good results. It can be used even up to 90 meters, as was the case prior to 2002 earthquake code. Until 1993 and 84 code, this was used up to 90-meter high buildings in the country. Okay. Now the horizontal distribution of the shear, once you know the base shear, we can calculate the design story base shear in any story to the various elements of the vertical lateral resistance element in proportion to the stiffness. Vertical distribution is given by this formula Q WHI square upon summation WHI square VB. VB is the base shear, which you computed earlier, and Q is the lateral force that we apply on each floor. Okay, and this, remember, this WHI square upon summation WHI square, this square tells you that the distribution of shear on a building in Indian code is parabolic. Okay, American code gives you the distribution in terms of WHI upon WJHJ. Okay, so there they assume a linear distribution in the first mode, whereas in the Indian code, we assume a parabolic distribution in the first mode. Okay, coming to the response spectrum. What is the response spectrum, or what is the response spectrum? The representation of the maximum response of a single degree of freedom system having certain period of vibration and damping during a given earthquake is referred to as a response spectrum. The maximum response of a single degree of freedom system, that is maximum absolute acceleration, maximum relative velocity, or maximum relative displacement, of a single event system is plotted against the undamped natural period for various damping values. The velocity spectrum is related directly to the peak state energy stored in the system during an earthquake. This is a very important parameter. The velocity spectrum is related directly to the peak state energy stored in the system during the earthquake. So kinetic energy Ke is given by half mv square. We all know from the basic principles of physics, half mv square. mv is the velocity, m is the mass. State energy is, we know very well again, that state energy is half Ku square. K is the stiffness, U is the displacement. Okay, if the maximum displacement is d, then this is equal to half kd square, and the maximum displacement of a single differential system and the velocity are related by the formula d is equal to v upon omega. Okay, so half kd square is equal to half k v upon omega square is equal to half mv square. So whatever state energy is given to the building, it is dissipated by the state energy produced in the various beams and columns through deflection. Okay, so dynamic analysis can be performed using the design spectrum given in figure 1 for 3 different types of soil: hard soil, medium soil, and soft soil. This is the spectra given in the Indian code. Okay, the first is the spectrum given in the top is meant for static analysis, and the formula figure given in the B in the lower part is for response spectrum method analysis. Okay, this spectra here, this is based on various earthquakes recorded in India in the last 50 years or so. Okay, most of the earthquakes have occurred in the northeast, that is northeast of India, and in Himalayan region or in Kashmir. And based on that set of earthquake, which is they had about, I think they used, out of those, they used 8 Indian earthquakes. Himachal Pradesh earthquake 86 I have given a list of here. So there are total 92 records, 46 sites into 2 components for Rockies, 57 sites into 2 components, 2 lateral X and Y, 114 records for stiff soils. Okay, so based on that analysis, they developed this response spectrum, which is available in your 2016 code. Now coming to the response spectrum method, how do we really apply response spectrum method in our buildings? As I told you, the building may have n degrees of freedom, and we simplify it so that we only consider p degrees of freedom, not n, to make our life easy. So how do you select the number p? We select the number p, saying the number of modes is selected so that at least 90% mass is excited for a reasonable accuracy. So p is such that you calculate the total modal mass corresponding to the p modes. You find that the summation of the modal mass is at least 90%. Okay, and if 90% mass is there, then we assume that it's going to give us fairly accurate results using the dynamic method of analysis or modal analysis or response spectrum analysis. I'll just give you very quickly what are the detailed steps, because these you will not find in the code, and it may be interesting how to apply the detailed steps on a building. So first step is estimate or assign preliminary sections to each beam, column, masonry, and RC wall in the building. You also have to assume certain type of foundation, whether it is raft foundation or isolated footing or pile foundation. So depending upon the soil analysis and the total weight of the building and the approximate earthquake analysis, you will design the foundation of the building, whether it is, as I said, isolated footing or raft foundation or pile foundation. Okay. Then you compute lumped mass at each floor level. The inertial force is applied at the center of gravity of each floor. The direction of the response spectrum is specified along X, Y, or Z direction. or even all the three directions simultaneously if required. So as far as the earthquake software is concerned, which is based on this equation 6, mx double dot plus cx dot plus kx equal to minus my double dot. So y double dot is the ground acceleration. Okay, so you can apply this earthquake y double dot horizontal x direction, horizontal y direction, and vertical direction simultaneously. So as far as software is concerned, it is capable of handling all three earthquake inputs. Okay, so it's your choice whether you want to apply only along x direction, only along x and y direction, or x, y, and z directions, all three together. Okay, the 3D dynamic analysis takes care of the horizontal and vertical distribution of the lateral forces on the entire building, assuming that the floor diaphragm is very, very rigid. Okay, the equation of motion is given by this equation, and we have already seen how to simplify this equation and obtain the eigenvalue values, that is frequencies and mode shapes. Okay, that part I just discussed earlier. So we carry out an undamped free vibration analysis to evaluate eigenvalues and eigenvector, that is natural period of vibrations or natural frequencies of vibrations and corresponding mode shapes in the first P modes. Okay, now number of modes. The number of modes, as I mentioned here, is such that the total modal mass summation is at least 90% of the total mass. Okay, here this formula given in equation 7 tells you how to calculate the modal mass in each mode. So R tells you the mode shape, whether it is first mode, second mode, third mode. So R is equal to 1 is the first mode, R is equal to 2 is second mode, R is equal to 3 mode means third mode, and R is equal to P means Pth mode. Okay, so you calculate the mass M in first, second, third, fourth up to P modes, find their summation, and this should come out to be 90% of the total mass of the building. Okay, you calculate the mode participation factor MPFCR, and this is the formula, and these formulas are given in the IS 1893 2016 code. Okay, so and they can be derived exactly by using the principles of dynamics of structures. Okay, some of you may, if you wish, you can refer my book on dynamics of structures, and there I have given the detailed how to derive these formulas. Okay, so they are based on sound principles of dynamics of structures. Okay, so you calculate the designed horizontal acceleration spectrum in the RS mode of vibration corresponding to the natural period of vibration in the each mode. So you calculate what is the desired lateral force at each floor in each mode by the following equation number 9. Okay, and this equation number 9 is same as given in the earthquake code 1893 part 1. Again, this is based on the sound principles of dynamics of structures. It has been derived there in my book. Then we can calculate the story shear in each mode by this formula. Again, this formula also given in the code. Then modal combinations. Okay, there are several ways to find the summation of various modes to get the net force for bending moment, shear force, axial force, and net displacement in a building. Okay, so you can use this formula. This formula is known as Cqc method, that is complete quadratic combination, Cqc. Okay, and I will not go into the more details now because this formula is again given in the code. This formula has been derived by some person, and somebody can refer to that formula. And rho ij is the cross correlation coefficient. Okay, that is what is the correlation between first mode and second mode, first mode, third mode, first mode, fourth mode, and so on. And beta is the frequency ratio of any two frequencies, omega I and omega j, and xi is the damping ratio. Okay. Alternatively, if the modes are not closely spaced, if they are far apart, then SRSS method of mode superposition may be used, and SRSS means the square root of the sum of the squares. This is again a very powerful mode superposition called SRSS, this formula given by equation number 13, this is how actually it reads. It is the square root. SR is the square root of the summation of the squares of the response quantities, that is lambda. Now, lambda may be axial force or story drift or shear force or bending moment or the deflection. Closely spaced modes. How do we define what is a closely spaced modes? In order to verify which of the modes are closely spaced, the following criteria can be applied. Omega j minus omega I upon omega is less than 0.1. Also, 1 is less than I, less than j, less than p. Okay, so this condition is satisfied, then you know that it is a closely spaced mode. That means any two consecutive modes, third mode, fourth mode, second mode, third mode, first mode or second mode, not first mode and fourth mode. No, we're talking about two consecutive modes. So whether they are consecutive modes, whether they are closely spaced or not, that is decided by this equation number 14. Okay, and then we can calculate the earthquake force, lateral force on each floor, or the story shears on each floor. Then we can carry out a 3D dynamic frame analysis for the dead loads, live loads, and lateral forces in each mode and get the member forces. And then response quantities are obtained by mode superposition method. Okay, we have checked the frame for story drift because we have to make sure that the relative displacement between any two floors, any two stories, consecutive stories, should not become too much. That means the people living in those floors should not be scared of the earthquake. They should not even feel that there was an earthquake. Okay, unless the earthquake happens to be very, very severe. Okay. Now, another very important factor is the analysis for torsion. Torsion is a very, very important factor in earthquake, and most of the buildings that have collapsed all over the world, whether it is Japan, whether it is California, whether it is India, whether it is China or Italy or Iran, you find that torsion is responsible for most of the damages, whether it is steel building or it is a RC building or even a masonry building. Okay, the analysis torsion may be carried out either statically or dynamically. The detailed method of analysis for 2D as well as 3D is discussed in a paper by one of my students, Satish Annigiri, in 1994 as part of his PhD thesis. A point of application of the earthquake force. The static force is applied through a point eccentric to the center of mass at each level, at each story. The eccentricity of the applied force is given by the following sets of two equations. EA is equal to 1.5 E plus 0.05 B and EB is equal to E minus 0.05 B. Now this set of equations is again given in the 1893 code. Okay. In most of the international codes, in the first equation, 1.5 factor is not there. They are using EA is equal to E plus 0.05 B or EB is equal to E minus 0.05 B. That means there is no amplification to the E, which is known as structural eccentricity, and that is defined as the eccentricity between the center of rigidity and center of mass at each floor. Okay, this is also defined as eccentricity between the shear center and cumulative center of mass at each story. So there are two ways to define it. Both definitions are correct. And in the Indian code, somehow they chose to use this formula 1.5E. Although in the 2002 edition, all of this equation was there. In 2000, there was a overriding factor. There was an overriding clause which was issued later on through an amendment to 2002 code, which said that if you are carrying out dynamic analysis, then the factor 1.5 may be taken as 1. But somehow, in the 2016 edition, they have withdrawn that simplification, which was a great simplification, without making any difference as far as the safety of the building is concerned. Because this fact formula, E plus minus 0.05 B or E minus 0.05 B, is already being used in most of the international codes. Okay, and our codes are not our original codes; they are based on copy and paste from international codes, other international codes. Therefore, I don't see any justification whatsoever for using a factor 1.5 except to make the life of the designer difficult. Okay, method to account for, so this factor 0.05b is known as accidental eccentricity. Okay, so it is assumed that even though the building may be fully symmetrical in plan, in elevation, with respect to mass, with respect to geometry, with respect to stiffness, is still, because of the soil conditions, because of the earthquake component, it is possible that still there may be some torsion in the building. So we are extremely cautious about the presence of torsional mode in our building, and therefore, although the building appears to be fully symmetrical, we still analyze it for some small amount of design eccentricity called accidental eccentricity, which is taken as 5% of the width of the building. So B is, what is B? B is the width of the building normal to the direction of the earthquake. Okay. So if you know what is the maximum largest dimension of the building, you take 5% of that and you calculate what is the accidental eccentricity, and you apply this earthquake force at that eccentricity and analyze the building. Okay, there are two methods to account for the accidental eccentricity. One is the static method for accidental eccentricity, which can be done by static analysis, which is very easy. Other is the dynamic analysis, which is equally easy, provided there is no amplification factor to the first component, that is factor 1.5 is not there. That factor 1.5 is taken as 1. So the mass is shifted by plus minus 0.05b on either side of the center of mass. Dynamic analysis are carried out, and the envelope is taken as the 3 dynamic analysis. And the problem here is the loss of the sign in the mode superposition. This I will take up later on. Now here, another very important factor, loss of sign in response quantities and static equilibrium. In dynamic analysis, in the process of mode superposition, the sign of the response quantities, that is member forces, axial force, shear force, bending moment, sign is lost. That is whether the force is tension or compression, hoggy bending moment or saggy bending moment. Okay, that sign is lost because of the superposition, because we are using either SRSS method or Cqc method. So you can see here, we are using this formula square root, and by taking square root or by taking square root here, the sign is lost, and therefore, when we combined the dynamic forces on the static forces, that is static under the dead load and live load, when you apply to that the force due to earthquake, our sign of the earthquake force is lost. So what all softwares are doing, they take static member force and plus absolute dynamic forces. So all the dynamic forces are added directly to the static member forces which are with their original sign. Second time, you take the static member forces and minus times all the absolute dynamic forces. So you get 2 sets of forces, one with static member force plus absolute dynamic force, and second is static member force with minus absolute dynamic force. Okay, so for that we design a building. Sometimes you may find that the results are a little awkward or maybe absurd sometimes. You have to use a judgment, check it more detailed, how the forces were combined, and then you can design it. Now remember one thing, in such a situation, the joint equilibrium of member forces is not valid anymore. That is, you can, if you try to apply the moment equilibrium at the joints, it will not satisfy because of the loss of the sign of the dynamic forces. Okay, so don't even attempt it and don't get confused if the equilibrium is not satisfied. No, it will not satisfy. It is not supposed to satisfy. Okay, so we design this force like this and carry out the further design of the building. soil structure interaction. Now, a lot of people ask whether soil and structure interaction should be taken into account, and if yes, under what conditions. In most cases, there is no need to take into account the soil structure interaction, even if soil is soft. Okay? But if the building is very important, then you may wish to carry out a soil structure interaction. Otherwise, there is no need to carry out soil structure interaction. In the case of hard soil, the interaction can definitely be totally ignored. So the recommendation is, if your building is very important, and the soil is soft, okay, out of three categories: hard, medium, and soft. If building happens to be on soft soil and the building is very important, you may wish to go for soil structure interaction. Otherwise, for routine buildings, there is no need to carry out soil structure interaction. Okay. Now, another important thing is computer-aided analysis. We carry out the building analysis using StatPro or ETABS or any other software. Okay. It is strongly recommended that the user must fully understand the implications of the various commands and options in each of these two very powerful software. The result must be carefully analyzed and verified so as to avoid any unpleasant situation. Okay. These are very sensitive softwares. If you do not understand the software, if you have not read the user's manual, because most of the people don't care to read the user's manuals. Okay. So I strongly advise, please go through the user's manual of each and every step, whichever software you are using. Okay. You don't have to use any of these two, maybe some other software you are using. So please go through the user's manual of each of the software that you are using. Understand what is the implication. Okay. Now, another very important thing is, although these softwares may claim that they are using or they are following 1893 Part 1 2016 code, okay, or IS 456 code, or IS 13920 2016 code, okay, or IS 875 Part 3 wind code, okay. But you may find, if you go in the interior, of the software, they are mentioning very clearly in the user's manual that so and so clause is not being followed. Okay. They mention very clearly in the user's manual that so and so clause is not being followed either in the analysis or in the design. And they will tell you why they're not following it or what they're doing if they're not following this clause. Okay. So please, first of all, don't be in the impression that these softwares or any commercially available software, because those softwares are basically written for either American market or European market. They are not written for Indian market. Okay. So their main concern is Europe or America. Okay. So they are very particular. And moreover, in those countries, the code is based on rational thinking, rational analysis. Okay. In India, as I told you earlier also, our codes are based on copy, paste, and edit technology. We don't have any of our own Indian original research. We just copy some part from here, some part from there, some part from there, and then use our judgment to make some modification to look as if we have done something original. And in that process, we lose the logic. And if you lose the logic, obviously, software cannot help you. Okay. Software will help as long as there is a logic in your analysis or in your design. If the logic is lost because of your copy paste and edit technology, then you can't blame the software writers. Okay. So please be very careful. Don't be misled by this statement that these softwares follow Indian codes. They do not follow all the clauses in the analysis and the design, because those clauses are impossible to follow. Okay. With this, I would like to close my presentation here. And if you have any questions, please feel free to ask me.
So thank you, sir. And thank you for the warning, basically, of the softwares. We really don't go deep into what has been written to the softwares, and we blindly follow the softwares. That happens. So this warning was really a wake-up call for us. So now for participants, I would request either you use the chat box or you can directly ask him questions for any of your doubts to be cleared. So now over to participants.
It's okay, no problem.
Yeah, nobody yet. So participants, shall we call it a day? I hope it is, sir. As there are no questions, we would remind the participants that this is only part one. Okay, there has been a question, sir, in the chat box.
No, see, the question is, why should we use formula for the fundamental frequency for steel building if we are using software which directly gives the value? Please note, you have to read the code. Code says, even if you are using a software, the base shear that you compute has to be based on empirical formula. Okay, that is the reason why we are forced to use the empirical formula, that is 0.085 h to the power 0.75 for a moment distance steel building, even if you are using software, because software will generally give you a larger time period, that means a smaller force. Okay, therefore it is the code which is forcing us to use the approximate formula for the fundamental frequency of a steel building. Okay.
So any other questions? Sir, it seems there is no more questions. Would request the participants that this is part one of the 2 days program.
There is, Manu sir, there is another question.
Okay. Where is it in the chat box?
Yes.
I don't have the formula. I don't have the second question on chat box.
No, I also don't see any.
You can ask.
Yeah, anybody can ask also.
See, as far as this RCC building with steel bracing is concerned, if the formula is not given in the code, you can't do anything about it. Then you have to use your time period given by the your software. Okay.
Yeah, so participants, shall we call it a day? This is basically the day one of this course. Day two will be on 29th of July. So in the meantime, if you have any questions in mind or some question comes out within this meantime, there is a second day when you can express your questions.
There is one more question. I can
One more question there, sir.
Yeah. See, I think the participant should understand one thing. Let us first understand what is available in the code. Okay. You're asking questions which are, of course, welcome. But you're asking questions, which are beyond the code. So the first question was, how do you analyze a building where, you have a RC building with steel bracing members? Of course, code doesn't give you this formula. Now, the next question that I have received is composite construction. Some floors in RCC and rest in steel. Okay. For such special buildings, these are special buildings, and for special buildings, there is no formula given in the code. Because see, code will remember, code has limitations. Code cannot be a handbook. Code gives you only for those buildings which are most frequently used in the practice. Okay. So most commonly used buildings are covered in the code. And if you are happening to use a special building, then obviously you have to refer to a specialist literature. Okay. The next question I have received is, I don't understand this question. Are there any guidelines for torsional design of axial members? What do you mean by torsional design of axial members? If a member is axial, how can you have torsion?
I think, sir, the question needs clarification.
Yeah, I mean, please think about this question, what you're asking. Torsional design of axial member, what does it mean actually? I don't know. I don't understand your question, please.
Okay, sir, I don't find any other question. Let us conclude today's program. Thank you very much, participants, and thank you very much, Dr. Jain, for delivering this codal provisions. So this is part 1. Part 2 will be on 29th of July at 3 p.m. So with this, we thank each and every participants, and we will be sending you the link again on 27th or 28th of July, so that you can join the next course of the program. So thank you all, and good night.
Thank you. Thank you.
Thank you, sir.